So this talk is also about WebAssembly, maybe unsurprisingly, but it's more focused on the mechanization aspect. I do wear a couple of different hats within the WebAssembly community on the industrial side. I have a contract to do standardization of various things related to WebAssembly concurrency. I will not be talking about that here. This is also not a relaxed memory talk, except for one line of one slide. I really am going to be talking just about my work on mechanizing the WebAssembly specification. So how did this start? Well, when I was a PhD student, and this is kind of me partying at my first Halloween party in Cambridge, I got really excited about WebAssembly because Andreas showed me the draft specification. And from my previous experience looking at the awful situation around ASM.js and so on, I instantly knew WebAssembly was going to be really exciting. So I thought, I just want to mechanize everything, because I was also doing Larry Paulson's Isabelle course at the time, and I got really excited about just smashing all of these things together. And it kind of ended up happening because the industrial WebAssembly people published the first draft specification in this PLDI 2017 paper. And then I was coming along and kind of mechanizing it, and there was this CPP 2018 paper, basically, of this draft semantics. And it was wonderful. I managed to prove type soundness, which was a statement they had essentially conjectured in the first paper but not proven. And then I was able to prove it and discovered a couple of bugs. As Andreas said, no major bugs in the WebAssembly semantics. But what's considered a major bug from an industry point of view is kind of not the same as from an academic point of view. So we were quite proud to discover these errors in the semantics through the mechanized proof. And I do want to explicitly say, at this point, Peter Sewell was my supervisor, and I'm very grateful for his support during the PhD. Okay, so what happened next? Well, then we actually managed to get a W3C published formal standard, and this was essentially all of the rules of the 2017 paper, plus a bunch more to discuss other phases of WebAssembly execution that weren't explicitly part of the original draft semantics. And I teamed up with Philippa, Jean, Martin, and Rao, several of whom are in the room, to do two mechanizations of this WebAssembly 1.0 semantics, one in Isabelle and one in Coq. And this seemed to make sense to us because Coq has a bunch of libraries you might be wanting to use. For example, all of the floating point and integer stuff out of CompCert, and we were thinking about iris integration and so on. And Isabelle also has some nice things, especially Peter Lamek's imperative whole allows you to do some pretty cool monadic stuff with mutable state. So I was quite excited about the Isabelle mechanization. They were quite excited about the Coq mechanization, but these were both meant to be mechanizations of WASM 1.0. And at this point, I also became a co-chair of the W3C WebAssembly community group. So this is my industrial hat doing work on the standard. And I have mostly failed to link up my industrial work to my academic work in terms of kind of papers. There's a little bit on the concurrency side, but I won't be talking so much about that in this talk. And you'll notice here, my ambitions have become a little bit tempered. I'm no longer saying I want to mechanize every future WebAssembly feature. I'm kind of just about saying, well, okay, we now have the W3C stamping versions of the WebAssembly spec, and I think we can mechanize whatever version they stamp. And then in the intervening years, I did a whole bunch of collaborations with different people who were interested in using these mechanizations. We had some kind of cryptographic type system stuff with some people from UCSD. Had WASMref Isabelle, which was this fast interpreter using Peter Lamek's exciting imperative whole monadic library. And we had Iris WASM. So we got both the best out of Isabelle and the best out of Coq with these papers. And at this point, my thought process was pretty much, I need to secure a faculty job. I wasn't kind of having high-powered ideas about mechanizing all of WebAssembly anymore. But all of these were pretty interesting and kind of motivated that these mechanizations were useful and actually exciting to people. And now kind of today, so as Andreas said, in 2022, and well, depending on how you count the process of W3C ratification, we have WASM 2.0, which brings in a whole bunch of new features. And we kind of thought, well, we should mechanize this, right? So right now, only the Coq mechanization is updated to WASM 2.0. And we don't have WASM 3.0 yet. So in some sense, I can say we're not behind, but we're definitely not having any kind of ambition of being ahead. It's more the case that I'm hoping I can get the Isabelle mechanization up to the Coq mechanization. We can say, okay, at least we finished WASM 2.0 before WASM 3.0 was released. And you'll notice I'm also no longer smiling. So this has, clearly become a little more difficult for me to handle. So there are a couple of different kind of ways we might try and tackle this. SpecTech is clearly kind of tackling one side of this, the process of going from the spec document to the mechanization. But then there's also the process of going from the mechanization to the type soundness proofs, which is one of the big things we want to run alongside each future feature. And yeah, we're scared of WASM 3.0, which is actually really, really big, and does a lot more violence to the WebAssembly virtual machine than WASM 2.0 did, so we'd expect a corresponding larger amount of refactoring in the proofs. And so this kind of prompts me to start asking wider questions about the sustainability of this project and the scalability of WASM semantics, specifically in relation to mechanization. So before I get into the details of how we've been thinking of tackling these problems, I want to kind of, in the spirit of what Peter was saying, give a sense of how the industrial WebAssembly community has been reacting to this work. And I would say, broadly speaking, they've been almost suspiciously positive. We've got lots of questions like, can we include a mechanized semantics in the official specification repository? Can we require verification of every prospective WASM feature? And how do we create a verified WASM runtime? And I would say, actually, my job in most of these situations has been to do expectation management and not kind of foolhardishly promise way too much that I then can't actually produce. So broadly speaking, I kind of answered the first question by saying, if I did this, for sure the mechanization would have bit rotted in the repository. And I think that's pretty clear now, considering WASM 2.0 is almost old news and we're kind of progressing towards WASM 3.0. Back in 2018 or so, if I had accepted this idea of having the mechanized semantics in the official repository, I think we would have ended up in quite an embarrassing situation where it would have looked very out of date in comparison to everything else that was going on there. And also the maintenance responsibilities become a bit unclear. If you put this thing under W3C, really I'm still the only person at the time writing Isabelle code to keep this thing updated. So there's a little bit of a clash between the W3C process for updating the standard and whatever process we'd be using for updating the mechanization. So I think I made the right decision in saying, oh, it's too early for this. Thank you for asking, but I don't think I can give you what you want. And similarly, can we require verification of every prospective WASM feature? Well, again, you kind of need an up-to-date mechanization if each feature is building on top of each other. And it's also really, really bad politically if you end up with a situation where the proof is the only thing that's blocking a feature from moving forward. That's an incredibly embarrassing situation. And the minute that happens is the minute all the industrial people never want to look at formal methods again. It's been hard enough holding up features just on the basis of the specification being written formally. Even that caused a few murmurings. But if it was not just the specification, but the proof that was blocking stuff from moving forward, I think people would be pretty unhappy with us. And that definitely would have happened if I had kind of accepted these excited early proposals to put the mechanization more clearly in the standard.
Although I would say that in practice, it's usually the implementations that block progress, right?
I would say that's the case the majority of the time. But there were one or two big ticket features where the spec was the slowest thing, and the proof would certainly have been way slower than the spec. In particular, I'm thinking of threads as the big one, as you're aware. That was a situation where the formal model was an order of magnitude more complicated than people's intuition for how the thing should work. And I'm not saying that every feature would have this problem, but if even one or two very important features have this problem, everyone gets very unhappy and you're kind of suddenly the villain. And then how do we create a verified WASM runtime? Well, how many years are you willing to wait? We kind of have this verified interpreter that's very slow. I don't think that's what they mean by verified WASM runtime. These are people who are used to working with a kind of portfolio JIT compiler with 3 optimizing tiers. And getting all the way to that would require quite a lot of research, so it's not the thing I can kind of commit to casually. And then the one relaxed memory thing that I'm going to bring up in this talk is I had one very scared Google compiler engineer approach me and say, please can you write the thread specification so we don't accidentally introduce out of thin air behaviors with our optimizations. Which is very funny, because I think this means all of our academic discussion about thin air has kind of penetrated into industry and really scared a lot of them. Of course, I think this is a total inversion of responsibilities, because it's not the individual compiler writer's responsibility to not write an optimization that does thin air. But I thought that was pretty funny. Question?
So, like, positive response from industry is fabulous. Does this turn into actual resources they're willing to put into this project? Or is it more like, we are willing for you to do free work for us to do this?
Yeah, at this point, it was definitely more from that point of view. I would like to, I think with things like SpecTech, we can potentially get on a firmer footing where if they're willing to fund SpecTech from the point of view of it producing the specification, there's some amount of cross-subsidy that happens where the SpecTech resources also maintain the mechanization. But that's kind of my future fantasy. Certainly at this point, it was very much, we're willing to bless the thing you're doing, but you have to keep on doing the work. It wasn't them promising any additional resources.
Can I make a point there?
Yes.
So also, Andreas was talking about funding, and that this is in a rocky situation from this point of view. You're trying to entice people in all the time. So in particular, we've got this meeting in 2 weeks' time. Actually, anyone got any ideas about how one can even begin to progress that and work out what even is the ask for this sort of thing? We don't really know. So how does one do this?
Yeah, so it's interesting that from my point of view, the community story has been everyone's really excited about this, almost kind of too excited. And I'm having to say, well, I can't actually give you the things you want. Maybe if you gave me a lot of money or a lot of kind of expert engineers, I could do it. But that's a level above just asking them to bless it, which I think is already something we're often pursuing from industry and not getting in a lot of circumstances. Oh, yeah, so my answer to the compiler engineer was, yes, you've totally misunderstood the point about thin air, but I appreciate that you're scared about it, which is, you know, better than we might have expected otherwise. Okay, so yeah, themes. The WASM community broadly believes our story and is in some sense almost too ready to accept our contributions. And the consistent problem has actually been they get very excited about something and then you have to get into the question of can you feasibly deliver it with the resources you have? And you know, you need to exercise some responsibility in turning down some of the things they've been asking for. And I think I've broadly struck the right balance, although maybe if I'd been braver, we could have already had a mechanized WASM specification that was normative. I judged that I couldn't keep that up to date, and I think I was pretty much correct in that. And so kind of the current thing I'm thinking about with my mechanization hat on is how do you reduce the cost of delivery for this whole story? So if someone approached me again and said, we really want the mechanization to be normative, how would you even get close to delivering things at a kind of velocity that lets you not be embarrassed in front of them, essentially? And there are a lot of different moving parts to this. So I'm sure you're all familiar with the process of how a kind of not mechanized industrial standard becomes something mechanized. You start with all of the industry people, excuse me, let me not have that arrow yet. You start with all the industry people who kind of write the specification, and at least in WebAssembly's case, we're lucky that it is pen and paper formalism. So that's quite nice. That already saves us the process of interpreting some nasty English spec. But then we have to look at this very hard and turn it into our mechanization. And then we have to look very hard at the mechanization and write lemmas, and maybe look at the properties this specification said the formal semantics should have. And then we do all of our proofs, we make our kind of verified interpreter, we make our program logics, and at each stage, there's kind of a lot of work going on. And when we're thinking about starting from a mechanization and keeping the proofs updated, we're kind of in this world here. And one thing I should highlight is we have been quite lucky in that in doing these formal proofs and creating these artifacts, we have had cause to feed back and change the specification on the basis of, you know, bugs and errors we've discovered. Not show-stopping bugs, as Andreas said, but I think things that as researchers we can be pretty proud of. But there's also this question of, you know, how do we make this aspect faster? Right, so stage 0 is actually having the formal specification in the first place, and the process of turning that formal specification into the mechanization that we then do proofs over. And I'm not going to totally recount Andreas's SpecTech story here, but this is basically where we're hoping SpecTech will help. We're essentially tricking, from the mechanization point of view, the companies into writing our mechanized spec for us, and then we're at least reducing that amount of the work. So you kind of get this situation where, you know, yes, we're generating the specification, but the important thing for me is we're generating the mechanization, which we can then do our proofs over. And that's already reducing, I think, the cost of this process quite a lot. I would say when a new feature gets added to WASM, and I try and percolate it through the definitions and proofs, I would say often more than half the effort is updating the definitions themselves. The proofs often fall out pretty mechanically, just from chewing up 200 inductive cases with a simple tactic. But just actually the process of translation can be quite annoying, because you have to decide, what am I refactoring, what am I rewriting from whole cloth? Getting some kind of automatic generation from SpecTech makes that situation a lot nicer. And then yes, even if we get that story, kind of in a nice situation, which I'm not going to go into too much details about, we still have the problem of, okay, SpecTech has spat out a model for us, How do we do our interesting proofs in a kind of more tractable way? And I don't have a total kind of covering answer for all of the things we should do here. But I have been kind of thinking at the very least, well, if we've got our mechanization, and the one thing we really believe we need to keep updated is the type soundness proof, how can we do that in a slightly more tractable way? And the rest of this talk is going to be about one specific approach for doing this, and for one specific approach for doing one specific part of this, which we think is helpful as a building block, clearly not the whole story for making this thing very easy, but one of the kind of things I think we need to think about if we want to reduce the cost of this whole endeavor. So these are the kind of, these are kind of the core things that we believe we need to prove or do on top of the semantics in order to say, okay, we have our mechanized semantics, and we've, in some sense, done all of the basic verification and validation we need to do to show that it's a good formal semantics. And for us, this was proving type soundness, which is actually given as a statement in the WebAssembly spec. Of course, they don't include the full proof. It's our job to prove that their statement is actually true. And we want an executable interpreter function that we've proven sound with respect to the operational semantics. And this is good, firstly, because, well, you want something that's executable and verified. There are a lot of different reasons you could want to use that, like as a fuzzing oracle or something like that. But it also allows us to validate the inductive semantics, because we can then run it on the test suite. So it's one extra way of making sure we've got our mechanization correct. Sorry, go ahead.
So the soundness of the interpreter, have you done that for the garbage collector?
No, we haven't. That is WASM 3.0, which from our point of view is something that's not published yet. We still need to do 2.0 up to this standard. We've mostly got it there for Coq. We need to do it for Isabelle. But we do think that the kind of things we're thinking about with a combination of spec tech and the proof techniques I'm going to describe now will be our path forward towards doing that. So that's kind of the immediate next step as far as I'm concerned, to do it for GC, which is this proposal, and threads and so on. But yeah, that will be a big pain. We're hoping to make it less of a big pain with these kind of techniques.
Well, I mean, I should say that actually GC, in terms of the semantics, is kind of trivial in terms of operational semantics. You don't specify that there.
Well, but in terms of the type soundness proof, it's definitely not trivial.
Yeah, the type system gets a bit more complicated because we're describing a more complicated memory layout. But there isn't anything interesting going on operationally there in the actual GC part. But you have these more complicated types now.
Yeah, so the two places this will turn up is the type soundness proof gets an order of magnitude more complicated, and also proving dynamic casts in the executable interpreter, correct, will also probably be fairly complicated.
Question. You mentioned several times that you have the top formalization and the Isabelle formalization that you're trying to have them both be apart. Is there a reason for this? Are you doubling the cost by doing it twice?
Yes, but we think both communities get something out of it. On the Isabelle side, as I was saying, there's all this work on the monadic stuff, which I think lets you really push the boundaries of very efficient, verified software, because you can do all of this mutable state update, and there are lots of libraries in place to make that tractable. And on the Coq side, of course, the community is massive, so we can't even envisage all the ways the Coq community wants to use our mechanization. But at the very least, we're very interested in the kind of iris integration and the compsert integration story. And clearly you need both mechanizations if you're going to appeal to both communities. That's another thing SpecTech will help with. If you're just writing the one SpecTech definition and spewing out both Isabelle and Coq, now you're no longer needing to worry about the cost of updating both mechanizations at once. But you do still need to worry about updating both proofs at once. And I'm not really going to go into detail with this in the slides, but we have this whole thought of, well, can SpecTech auto-generate some of the proofs in some kind of unified way, so you get like a skeleton out in both Isabelle and Coq to make this easier. So you're right, it may turn out that one of the ways we significantly reduce the burden of this is we just do it in Coq, because that's the bigger audience, and clearly it's a little further on right now, having 2.0 done already. I personally really like Isabelle, and I've benefited from, maintaining my Isabelle mechanization, so I'm going to try and keep Isabelle alive, and maybe I fail at doing that, and that might actually be a bigger time saving than any of the other things I'm describing in this slide. So yeah, you're right. It's a challenge, but I want to engage both communities, so I'm going to try and do that as much as I can.
So there are different reasons for doing this. I mean, from the point of view of the people in industry who just want mechanization, then, well, they just want one. But from the point of view of researchers, we want to understand, well, different ways of mechanizing the same thing anyway, and develop, we might be able to sort of inform one of the mechanizations by observing that we can do it.
Yeah, we actually had an early lean backend even, and Sam has started working on an actor backend as well. So part of the infrastructure is that you can have various backends with varying degree of production readiness or experimentalism.
I think I saw a hand.
Yeah, I mean, so COP is the 800-pound gorilla within the PL community.
Yes.
There is a very large, wide world outside of that who also are interested in the correctness of programs.
Well, I'd encourage them to write their own backends for SpecTech, which hopefully we can facilitate. And there is going to have to be a limit to how many we maintain ourselves. I can kind of take personal responsibility for the Isabel backend. I'd expect Philippa's group to take responsibility for the Coq backend. Sam's group maybe for the Agda backend, and maybe that becomes a way of scaling up the whole SpecTech story. Does that kind of make sense as a narrative?
Can I say, so there really is an opportunity here because of all that Andreas work that has got this embedded to a real standard almost before we start. So the point is to have it is a test bed or a playground for us lot, as well as something for an industrial standard. So for example, Andreas mentions just lightly about the test generation. Please test generation people come and play, because there's an opportunity.
So maybe this fits a larger question of how you migrate formal definitions from one prover to another. Mm-hmm. And you don't need to migrate the proofs because maybe it's sufficient to do the proofs in one prover and just migrate definitions to another prover. But this is a general question that comes back to the project. And so maybe instead of investing time importing the specification, you invest time in this with other researchers in this project of importing specifications from one prover to another. You could have a tool for doing this.
Yeah, so I guess I could tease apart what you're saying a little bit. So in terms of porting the definitions, the tool we're expecting to work for that is SpecTech, essentially, right? Because SpecTech will produce each of the definitions. In terms of things like the verified, so I guess by definitions you mean like the lemmas and so on that we're proving on top of the semantics. Yes, it might turn out that the world where we end up is actually you only prove these things in Coq, and if someone wants to use them in another theorem prover, you just axiomatize them there, which is something I've seen people in other projects doing. Or it might turn out that we can really teach SpecTech to produce a lot of this itself in some theorem prover agnostic way. Because actually a lot of the type soundness proof is a pretty mechanical unfolding of all the definitions. So maybe we get pretty far with that. I don't know yet. One thing I would say is for the rest of this presentation, I'm going to be talking about some techniques that would be useful even if we only did the proofs in Coq. So at the very least, this is still allowing that world to be a possibility. I'm not committing to something that definitely requires us to do the proofs both in Isabel and in Coq.
We actually had quite some amount of discussion about like what is the right infrastructure in this compilation pipeline to share between different backends and stuff, and this is very much like a completely open problem to us, right?
Yes, I should move on quickly, so maybe this is the last question.
So, I mean, kind of following up on Arthur's question, right? Yesterday, Dominique talked about this idea of sort of really focusing on what he calls these universal contracts, sort of language level properties as part of the language specification, in a sense sort of the same standing as these semantics of instructions.
Yeah,
Do you think there's a space to...
I totally agree with that. And in fact, you can write the definition of type soundness pretty much in SpecTech. And we're expecting to do that. So the only thing, even in this world where you're doing both the proof in Isabel and Coq, you're actually getting at least all the definitions that build up to type soundness extracted for free, and it's just doing all the proofs that link them to the semantics. That's the thing you have to do yourself. And it's already the case that the pen and paper WebAssembly specification has this annex stating the type soundness property. And we definitely think we can replicate that in SpecTech, and that should help people.
It also states various other properties, right? You also plan to mechanize those actually?
What are you thinking of? Are you thinking of some relaxed memory stuff, or
no, like about the type system, about like principal typing?
Oh yeah.
Like
so I guess this becomes more of a concern with the GC extension. So once we get to the GC extension, maybe this list gets bigger. But right now we're not there yet.
Yeah.
Okay, I should move on because up until now I've been talking very broadly about kind of big picture concerns. And for the rest of the talk, I'm going to be kind of much more narrow in one specific thing we've done to try and get towards addressing one specific concern for one specific kind of proof. But clearly this is just going to be one brick in the wall for the wide agenda of trying to make this whole thing more tractable. And to kind of set the scene, like I said, these are the 4 things we care about right now: the type soundness proof, the executable interpreter, and soundness of the interpreter. And in particular, right now we're defining our interpreter ourselves in Coq, for example, as this function that, takes a WebAssembly configuration, which I'm just expanding into its individual components here, and returns you a result that says, either I take one step normally, or I crash, or I do something weird. And then my soundness with respect to the operational semantics, in a simplified form, looks something like, okay, if the interpreter reports that it successfully took 1 step, that implies the semantics will take 1 step. So that's your soundness property. And just to blow up the definition of a result here, we have our normal result where you took 1 step, you have your value result where you've terminated, you have a crash result where you've done something unsound, which shouldn't happen if you give it a well-typed program. And you have these 2 auxiliary results here, which are to do with control flow in WebAssembly that kind of looks like throwing an exception. I'm not going to go into these in detail, but just know to handle WebAssembly's control flow, we also have to handle these strange cases. And this particular thing we were looking at was very much inspired by a challenge from Philip Wadler, who kind of came up to us and said, this isn't a new thing, but I think it's quite interesting, this idea that you can take a constructive proof of progress and preservation, the standard syntactic type soundness way, and you can kind of chain them together, since they're constructive, to get an interpreter, which is actually pretty intuitive, right? The process of establishing progress in a constructive setting is essentially showing you have a witness that kind of computes, starting from the start configuration, take 1 step. So if you have a constructive way of doing that, that's almost an interpreter already, and all that's left is to wire things up so you can keep repeated steps. And his challenge to us was, well, can you do this for your WebAssembly proofs? Because if you can, you don't need a separate verified interpreter anymore, which is quite nice. We could eliminate half the work. And so our initial results, well, this was a team of the 4 of us. Again, we're kind of mostly in the room. Is Stefan in the room?
Stefan's not in the room.
Stefan's not in the room, but Rao's in the room, I'm in the room, Philip is in the room. And before we were mechanizing these kind of 4 separate things, and it turns out, yes, Phil's idea does work. And you can take our existing Coq proofs of preservation and progress, which were almost constructive already. You can kind of mash them a bit to make them fully constructive. You can throw them into Coq's extraction mechanism, and you get out an interpreter that actually does run. So now, for free, we have the executable interpreter function and soundness of the interpreter, because as part of progress, you have to prove that your witness corresponds to an operational step. So now we're just proving these 2 things. And we found this very funny quote, basically saying that no one ever does this. But we did it, which is quite exciting, and it scaled to WebAssembly. So, from the point of view of proof maintenance, this is great. We basically eliminated almost 50% of the work, even just in terms of raw line count that we were doing before. And you can imagine this is quite a boon. Every time you're adding a new WebAssembly feature, you have half as many things to update. One immediate limitation we ran into, though, was if you actually try and execute this interpreter, it's really, really slow, because you've totally naively pulled it out of the constructive proof. And the thing that makes a beautiful, small constructive proof of progress is not the same thing as doing computationally the least work to take a step. In fact, to make a uniform progress proof, we often found you'll uniformly consider a bunch of cases you don't need to, which creates a smaller proof by line, but in terms of the actual computation you're doing behind the scenes, it's a lot more. And we discovered this pretty sad result, where if you just do an iterative Fibonacci function, which isn't even involving any recursive calls, and you just keep on iterating it, even just maintaining the proof term that you're kind of computing over to do a single step, you have all of these weird time complexity explosions that just, you're choking after an input of 150, whereas our old interpreter, which was pretty slow already, is still sitting, you can't even see how fast it's going, right? So that's really sad. We have an interpreter that runs for kind of like, 10-line examples and then chokes to death. So our next thought was, well, how can we kind of keep this sense that we're merging definitions together and not having to do redundant work, while keeping our proof, we want to keep our proof maintenance advantages, but we actually want a little more direct control over the structure of the interpreter. So we're not just at the mercy of, we did the proof this way, and now we're very sad. And do we really want to get into the business of trying to write a proof that's computationally efficient? It seems like a bit of a mess. So the thought was, how do we control the structure of the interpreter more directly, while still being able to merge this idea of doing type soundness and the interpreter? Sorry, go on.
Just a clarification.
Yeah.
When you say the iterative version, you're just taking the first 2 things and adding them together?
It's bottom up, yeah.
Yeah, and so this is linear.
Yes, exactly.
Okay.
This is really sad. So, Yeah, one of our, so we go into a little more detail about this in further work, but just intuitively, the reason for this is you start with a kind of proof term that says, I'm well typed. And at each iteration, because you're applying progress and then preservation, you're reconstructing the proof term that the next step is well typed. And you're not doing that in the most efficient way. So if you just kind of push through the structure of the proof term just keeps growing and growing and growing, even though at a computational level, you're just doing iteration.
Yeah, but you don't, does your prover not have any way to reduce this, or is
Yes,
it computational and it collapses it?
Yes, you can insert, well, it can do it automatically. What you would have to do is write lemmas that essentially recurse over the structure of the proof and recognize that it could have been proven a smaller way and then kind of collapse it back down. So we actually did some experiments with this, and you can kind of flatten the curve by inserting these lemmas that, you know, look at two equivalent ways of proving things and pick the smaller one once you've kind of done the inefficient thing. So there are ways of flattening this curve, but you never get anywhere close to this performance. You're still in kind of a sad situation. Go on.
So it's not really that surprising. I mean, you're starting from this declarative specification and trying to make it run fast. And to kind of go back to Peter's point.
I have a slide about definitional interpreters.
Yeah.
Hopefully we get to it before I run out of
If
time.
you go
But
the
yes.
other way, then
Yes. Yes. But you're totally right. So Phil's approach was kind of to recognize, okay, if you have progress and preservation, you get an interpreter for free. And we started thinking exactly in this other direction. What if we had a sufficiently fancy interpreter that kind of as part of its certification is carrying some information we need to prove progress? And then if we can successfully get this interpreter defined and well typed, that kind of implies progress. And so we still have this idea that we have one definition doing the work of two things in our previous mechanization. But because the thing we start by defining is the interpreter, we have a lot more fine-grained control over computationally what it's doing. So to look at what we mean by causing this interpreter to certify more things, making it more fancy, recall that this is our definition of a result from the point of view of just the naive interpreter we were working with before. You either kind of you take one step, you terminate, you crash because you were ill-typed, or you do some weird exception thing. Now we need to add a bunch of extra certifications. So this is now a dependently typed interpreter. It's kind of proof carrying. And the idea is, okay, well now, if we get a result, that's not just computationally the next configuration. It's also a proof saying this configuration was sound. And we get to take advantage of the way the interpreter is structured, because the interpreter is already having to do all of these case splits on the instructions, you know, to make sure it's actually following the semantics just computationally. And we can kind of piggyback off of all of that to make the certification very neat, and we only need to do a bit of work at each of the leaves. And similarly, if you've terminated, you can certify, okay, we're in a value that should have terminated, or we're in one of these terminal error values. And we also need to do some certification for the exceptional cases, but I'm not going to deal with that. And then the last piece of the puzzle that lets you get all the way to the certification of this interpreter implying progress for free is you also add this kind of contrapositive condition that says, okay, if I failed to take a step because I gave because I gave conceptually an ill-typed input, I have to guarantee that input really was ill-typed. So it really is, this is the contrapositive of the progress property, right? If I have an ill-typed input, I will fail to take a step, as opposed to, you know, hold on, I'm getting mixed up. It's, if I fail to take a step, I must have been ill-typed, which is the contrapositive of if I'm well-typed, I'm guaranteed to take a step. So that's the correct way of thinking about it. And mechanization makes sure we write it the right way round, whereas I'm just a human. Sorry, go on.
You're making it look like you have to do it with dependent types, but I have the feeling you can make the same approach by writing your interpreter and then having two lemmas on the side.
Yes, so that works in Isabelle, and that saves you a bit of work. Obviously, you're going from 3 definitions to 2, and here you're going from 3 definitions to 1, which saves you a little bit extra. Yes, so it's not one definition which is a third of the work of 3 definitions, but we do believe it's less than the work of 2 definitions. So you're right, it's not totally linear savings, but you know, anecdotally, we were actually pretty happy with this. It was very nice to just have one place where all the case splits happened, and then all the work for all the proofs you care about just happens in the leaves. That was quite neat. I think I saw another hand waving, but it's disappeared. Good for now. Okay, so this is kind of the thing we were looking at, you know, adding all of these certifications on, basically piggybacking off the structure of the interpreter to not only prove the interpreter sound, but also certify progress at the same time. And there is like quite a strong intuition these things should be related, because in Phil's case, you're going the other way. You know, for progress, you need a constructive certification that you can take a step. this interpreter is that certification. We just need to do the extra proof work to prove it's that certification to COG. So before we were mechanizing 4 things, and now we only need to mechanize 2 things. And we do still keep preservation separate, because as I said, WebAssembly is this inductively defined semantics. It is non-deterministic in some corners. If we wanted to really mash this all into one definition, we would need to prove the interpreter is complete with respect to the semantics, which is actually so much work to even actually make the interpreter complete with respect to the semantics, let alone prove it. We judged it was better to keep preservation separate, but we do get to combine a lot of things together. And just exactly the point that was made, the dependently typed interpreter is more complicated than any of the individual definitions it's replacing. But we certainly have a lot of intuition that it's less complicated than any 2 of the definitions, so we were pretty happy with our result. And this is the slide about intrinsically typed semantics and definitional interpreters, so we can have a little bit of a discussion here. So the distinction between what Phil is doing with this progress plus preservation implies an interpreter, and what we're doing with a fancy interpreter implies progress. The reason that's relevant is specifically because we have a separate inductive semantics. If you're in a world where your definition of the semantics is an interpreter with intrinsic types, there's pretty much no distinction between these 2 things. So this is an observation and a kind of trick we're only having to do because we're just slavishly starting in this WASM world with an inductively defined semantics. And it might be that, by looking at this work, the WASM community suddenly decides we should do a definitional interpreter instead. But until that day, we're kind of stuck optimizing against what the current status of their model is. Go on.
I still don't quite understand how that captures non-deterministic.
Your definitional interpreter would need to have some kind of choice monad, or it would need to exhaustively explore all paths. It's nasty. So that's one of the reasons I think in the literature, most of the time when people talk about definitional interpreters in this setting, they're saying this is great for deterministic languages and kind of hand-waving the non-deterministic side of things. It's certainly a much bigger question of how you do this nicely if the language really is non-deterministic. I think you can probably still find ways to do it, but in any case, WASM isn't doing it that way yet. 2 hands at the back, maybe Peter first.
Non-determinism, I naively imagined that you wanted to build a checker, right? Not a generic non-deterministic.
You mean for your, well, if it's a definitional interpreter, maybe unpack that a little more. What do you mean by generic interpreter?
I mean, what I would have thought you wanted was a checker that can take as extra input some clues from implementation phrases about how they resolve non-determinism.
Ah, I see. But by checker, do you mean you have the result you're aiming for, and you're kind of working backwards to see if that result was justified by the semantics, as opposed to the forward execution?
A checker of the WASM implementation behavior. So you have some
Yeah.
behavior to check whether it's legal or not.
Yeah, so that's actually a lot closer to our existing inductive setting, right? Because that's, you have both the input and the output, and you're trying to find a derivation which shows that output was allowed. So we're kind of already very close to that world, actually, with the inductive WASM semantics. That's kind of the definition of WASM reduction. This kind of rival intrinsically typed definitional interpreter world really is making a strong case that to define your semantics, you should actually define an interpreter which takes the input and computes the output. And that makes a lot of sense if you're deterministic, with more open questions if you're non-deterministic. So I mean, I think we have a reasonable justification for why WASM has chosen the inductively defined semantics, but I'm aware there are some definitional interpreter lovers in the room here, so I just want to make sure they're getting fair attention. Okay, sorry, you in the green shirt.
In my PhD thesis, I actually had a definitional interpreter for C with non-determinism. So what I did there is I let my one-step function return a set.
Yes, exactly.
The reason why this works is that I only had finally branching non-determinism in the one steps. And the different thing that you can do is some non-determinism might be internal. Let's say like in C, if you allocate these kinds of provenances or so, they're not visible. So you can just pick one and you can prove that they are invariant somehow, that you can relabel them. But these proofs are nasty. I don't know whether you want to do it.
Yeah, exactly. My kind of prejudice about this is it's totally doable to make a definitional interpreter for a non-deterministic language, but it's nasty. So I'm not too unhappy that WASM has chosen the inductive style. And then right back.
Yet another definitional interpreter fan, and maybe I'll also respond to John's comment here and say, maybe work in a type theory that is extensional rather than intentional, like F-star.
Yeah.
And we have the definitional interpreters for languages with threads. We're working in a choice monad. It works out. And The other question I had is, why are you doing things in this contrapositive style? Why can't you, take as a hypothesis
Because so this is a point, maybe, I hope it's in the next slides, but it facilitates erasure. So the point is, we don't want the actual typing term to be present in the extracted code. We just want it to run as fast as possible, right?
It's a prop, right?
It's a prop, but if you include it as a premise, well, I mean, I guess you could include it as a premise if you're very careful. It's neat to include it in the contrapositive style because then you're just doing all of the reasoning at the leaves instead of having to work out, okay, I did a case split in the computation, now how do I relate that to my premise and work out how to destruct that in an analogous way. So it's about proof engineering, really. You could have shifted it to the argument. You would need to be careful to make sure you never case split in a bad way that causes Coq to complain about extracting something that you're case splitting on in prop, because then you're not allowed to erase it anymore.
Well, yeah, you should be careful about that, but it's doable.
It's totally doable, but I think this is an easier way of organizing it where, by construction, you can't be case splitting in the wrong place because you're doing all the work in the leaves. But yeah, this isn't the only way we could have formulated this. I think there are a whole family of equivalent ways where we shift things on the left or the right-hand side of the implication. But we're pretty happy with this arrangement. So where was I? Okay, yeah, so this quote by John was actually meant to be kind of ironic because we're actually doing exactly the thing he wants people not to do in that we're really leaning into Coq's dependent types. I think what he's saying is true most of the time. We think we've just found one of the times it actually makes sense. So line numbers are kind of an awful way, I guess I'm a little over time, but I'll breeze through this. So line count is an awful way of motivating how good something is. I would also like to tell you the intuitive story that we were very happy to do all of our case splits once and then all of our work in one place. I think that's also an intuitive reason why this is a nice technique. But even by line count, our kind of story is borne out in terms of successes and failures. So the old WASM cert Coq, including all of the kind of proofs and so on we said we wanted, came to about 2,600 lines, not including a bunch of auxiliary lemmas that all of these approaches are using. I'll get to the pain of those in a second. Our kind of fill style progress plus preservation, make it constructive, turn that into an interpreter, that's the very smallest thing. And in fact, it's even a little smaller than this suggests, because this 300 lines is modified lines of the type soundness proof rather than new lines we had to add. So this is actually a pretty small solution if you only care about getting a really slow interpreter. And then our approach kind of sits bang in the middle. And in fact, I would say this line count is a little bit inflated because we wrote everything in a very vertical style. So something that was maybe 1 or 2 lines here turned into 5 very small lines here. But even so, we ended up smaller. And we were able to take advantage of this nice approach to update the Coq mechanization to WASM 2.0, which, again, purely subjectively, we found a very nice experience with this approach. And in fact, the line count for WASM 2.0 is only slightly bigger than the old style for WASM 1.0, which kind of has far fewer instructions. So that was quite a nice experience. So to get to the point about auxiliary lemmas, this is another brick in the wall for needing to make mechanization better. So to do any of these proofs, there are a whole bunch of baseline inversion lemmas you need to prove for kind of each case of the semantics. And we kind of kept them in a separate file, all of them used the same ones. But if you were updating the WASM semantics, you might need to go and fiddle with the inversion lemmas again. So that's another piece of work. And that's actually something I'm personally relatively optimistic that we can generate automatically in SpecTech, but certainly that work would need to be done in addition to this work, kind of the last mile of the proof. So not everything, not a complete story yet, but each of these things adding together, hopefully to give a better experience. And then in terms of benchmarks, just very quickly, this was Phil's approach. It's by far the slowest. It kind of shoots off into the distance here. This is recursive Fibonacci now, so you're also dealing with superlinear complexity in any case. And then WASM Ref Isabel was my kind of very fancy monadic interpreter that I did with Peter Lamek's imperative whole library. And that's just about the fastest. But our fancy interpreter in Coq, giving progress proof for free, when you extract it, you erase all of the proof manipulation. And in fact, you're able to optimize the representation of the interpreter so it's about as fast, at least within the same order of magnitude, as my interpreter that I optimized by hand in Isabel. So that's also a pretty nice result. There are some optimizations that our interpreter in Coq doesn't do, especially related to manipulation of the heap. So I could pick a different benchmark that would make me look really good, but we're picking one that kind of shows where comparable optimizations have achieved comparable results. And this is iterative Fibonacci, similar story. Here's the naive progress plus preservation kind of Constructive approach, shooting off into the distance, while everyone else, you can't even see them because they're still down here, and this is an explosion of that graph showing the distinction between them. And again, WASM-Ref Isabel, just about the fastest. The OCaml reference interpreter, which is currently a separate definition maintained by the official standards body, kind of just there. And then our optimized interpreter, just there. And this is again, I think, yeah, so that's not too bad. And also, because it's iterative, we're not expecting this to be showing too many differences between the two. Really, this is, again, just to illustrate the naive approach is unusually bad, even for pretty simple algorithms. So just top-level thoughts to finish up. There probably isn't one silver bullet to make all of our kind of story of going from the spec to the proof simple. But by looking at each stage and trying to do something sensible to optimize it, hopefully the composition of all of these things lands us in a place where we can tractably keep things up to date, even as WebAssembly explodes with all of these complicated features. And my final kind of thoughts would be, one of the things that makes WASM 3.0 specifically really scary as an upcoming feature set is it's really kind of the moment we've shoved through at once a whole bunch of things that are going to massively complicate the WebAssembly virtual machine. So we have reference types, which was actually part of WASM 2.0, which really complicates what it means for something to be a value in WebAssembly. Previously, you could only have simple int and float scalar values. Now you can have references. Then we have GC, which, as we already discussed, is going to massively increase the complexity of the type soundness proof and parts of the interpreter related to dynamic casting. Threads will maybe not make it into 3.0, but maybe 3.1. Obviously complicates the execution model and relaxed memory as a whole thing if you want to make an interpreter. And then the next big generalizations coming after 3.0, we have stack switching, which Sam Lindley is working on. We have ideas of generalizing the GC type system into type variables, some kind of form of generics. And there's also a proposal by Google to do memory mapped I/O, which would complicate the structure of the WebAssembly memory. And I'm hoping if we can get over the hump of these proposals, actually there aren't that many more that are going to be fundamentally changing the WebAssembly virtual machine. So hopefully if we can get to a place where all of these are nicely mechanized and all the proofs are there, we should actually be in a pretty good situation where the next few proposals are really just iterating on the foundations that have already been laid, instead of refactoring the whole thing. But we need to get past this hump, and that's why I'm looking at techniques for reducing the burden. I think that's everything. So thanks for listening. Sorry I've gone a bit over time, but so did everyone else.